Okay. Well, last time we wrapped up our really general discussion of sort of broad mathematical concepts, and we started talking about the next little bit, which is working with integers. And I'm going to continue on with that today, go over some things about prime numbers and all that, and modular arithmetic, and then we're going to talk about applications of that to cryptography, which I think is pretty interesting. Okay, so one of the things I tried to illustrate last time was this idea of proof by induction. So we talked about that, and I'll do one or two more of those today. And we noted that Euclid used induction to show that every positive natural number bigger than or equal to 2, so every n bigger than or equal to 2 has a prime factor, at least one of them. And also, he showed that by induction, and also that there are infinitely many primes. Which follows directly from that provable by induction result. And that's pretty much where we were at last time. And today I want to continue talking about some important stuff related to prime numbers and factorization, all that business. The first one, and this is a really important result, and this in some sense is the first day of any number theory class or any abstract algebra class. They prove this theorem. And this is one of those things, and those of you who had 2200 last spring remember, it's one of those things that I would recommend like writing down on a little business card and sticking it in your wallet, and like when you're really bored, just pull it out and look at it. You know, it's a good way to learn something. So I'm going to call it a huge important fact or something like that. Huge important useful fact. And it goes like this. If A and B in the natural numbers, and both of these things, well, they actually don't even have to be that one, have no common factors, then, other than 1, of course, because every natural number has 1 as a factor, then, and when I'm using the word factor and divisor interchangeably, by the way, through all this, then there exist integers, and got to be careful here because they're not natural numbers. One of them, at least one of them, has to be negative. So integers m and n. So note m less than 0 or n less than 0 is okay, such that ma plus nb equals 1. Now you may say, well, why is that so huge? Why is that so important? Why is it so useful? Well, you'll see when you go through this why it is. And this is easy to prove. I'm going to prove it. It takes like 1 or 2 lines. But first of all, I want to introduce some terminology here. If A and B are natural numbers, and both of them are bigger than or equal to 2, and they have no factors in common, we say that A and B are, and there's different schools of thought on this, coprime is probably the more modern term the more ancient term, but this is one that you will find adhered to slavishly by math professors, relatively prime. So what the huge important useful fact says that essentially that if a and b are natural numbers that are co-prime, then there exist integers m and n such that ma plus nb equals 1. Okay, now why is this true? So to see why the huge important useful fact is true, what do? Let capital I be equal to, and there's a reason I'm labeling it capital I, but I'm not going to tell you because it's not really important. This is going to be the set of all integers of the form ma plus nb, where m and n are also integers. So that's a big set of integers. Now, because I contains A and I contains B, right? Why does I contain A? Quickly, somebody tell me. Why does the set of all integers of the form ma plus nb contain A? Yeah. Yeah, Aiden is correct. M equals 1, n equals 0 gives me A, and n equals 1, m equals 0 gives me B. So note, A and B are in I, which means that at least there are some positive things in I. Okay, so what I'm going to do is let D be the smallest positive thing in I. Okay? And what that means is there are numbers m0 and n0 in the integers such that m0a plus n0b equals D. Now, I claim that D has got to be a divisor of both A and B. So D divides A and D divides B. This is notation we introduced last time for something being a divisor of something else. I'm going to show you why that's true, but for now, suppose we prove that. Suppose we prove D divides A and D divides B. How does that show? What does that show immediately? What? D is 1. Right. Who said that, Brian? Yeah. D is 1 because A and B have no divisors other than 1. Positive divisors other than 1. So, from which it follows from coprimeness of A and B. Okay, so how come? Why does D divide A and why does D divide B? Suppose, for example, D does not divide A. Note, we need to have D less than or equal to A and D less than or equal to B because D is the smallest guy in I and A and B are both in I. So, since D is less than or equal to A, what can we do? We can divide D into A. And maybe or maybe not get a remainder. So D less than or equal to A implies that you can find, let's call it K bigger than 0, such that A equals KD plus R. And R is between 0, or is bigger than 0 and less than A, and less than D. R is the remainder you get by dividing D into A. So R is the quote-unquote remainder you get when you divide D into A. And if you don't believe that, I remember Brian asked last time this question about, where is he? I saw him come in. Maybe he's left already. Oh, well. Oh, hey. I was looking for red instead of orange. Okay, but anyway. Okay, he has, why is this true? He asked something about very basic last time. This is something that I'm kind of assuming you know. And if you can't see why this is true, just think of it this way. If you take D and add it to itself and add it to itself and add it to itself and so on, eventually you're going to reach a point where one of those sums is less than A and one of them is bigger than A. And that's where you stop. You have that many D's come up almost to A, and there's a remainder of R. And that's a basic fact about natural numbers. Okay? So A is equal to KD plus R. And that means we can write, and this is where I always get a little confused. If I take KD plus R, I get K M0A plus M0B, that's KD, plus R is equal to A. If I move these terms over to the right-hand side and leave the R there, and switch sides so it looks nice, I get 1 minus Km0 times A minus Kn0 times B is equal to R. See that? But wait, that means that R is in I, because I can think of this as M1 and this as N1, and I have M1A plus N1B equals R. Therefore, that R is an I, and that's a contradiction. Why is that a contradiction? Yeah, because R is less than D. R is a positive thing in I, less than D. No such thing exists. So D is the smallest positive thing in I. Okay, conclusion. We started with the assumption D does not divide A, and we found that that led to a contradiction. That means D divides A. We do the same thing with B, and we find that D divides B. So you conclude D divides A. Same argument, except we do B equals KD plus R, or whatever, shows that D divides B, and the claim is true, and therefore D equals 1. End of story. Okay, now like I said first day, I'm not going to prove too many things in class because proofs are kind of tedious. But this is an example of sort of how easy it is to use sort of basic facts about integers and natural numbers and stuff to come up with huge, important, useful facts. Okay. So that, yeah, Erica.
I'm sorry, I don't know if this is a dumb question.
No question is dumb.
The notation you use, the line between D and A, is that D over A?
No. This means, yeah, let me put it over here. If I ever write something like this, say D divides A, that means, quote, D is a divisor of A. That was a piece of notation we did last time. All right, so that's a good thing. That's a good thing to know. And another good thing that follows directly from this, and I mentioned this at the very end of class last time, so another not quite so huge but also useful fact is the following. If A and B are natural numbers and P is a prime number, then the following condition is true. If P divides the product of AB, then either P divides A or P divides B or both. Okay? Intuition behind that is as follows. If you have the product of two natural numbers, you can think of like clumping them together somehow, right? And if P divides that product, and if it doesn't divide either one individually, then there has to be some way of dividing P up in a sense so that a piece of P divides A and a piece of P divides B. But primes don't have pieces. They're elementary particles of natural numbers. So that makes sense. Now, why is it true? It follows directly from this basic important fact. Let's see. Okay, so why? Suppose P doesn't divide A. Then, what is true about P and A? P and A are co-prime. They have no divisors in common other than one. How come? Why is it true that if P is not a divisor of A, then P and A have to be co-prime? Does anyone see why that's true? Nathan. It's simpler than that, actually. Have I learned your name yet? Okay, what's your name?
Victor.
Victor, okay.
Because P is prime, the divisor one.
Okay, and?
So they're only shared divisors could possibly be one.
Right, because P is not one such thing. P does not divide A. P's only divisors are 1 and P. Therefore, the only divisor of both P and A is 1. Aiden.
Is P necessarily less than A?
That's an interesting question. I have to think about that one. I think it's true. It's trivially true that P and A are co-prime. What if A is P and P is P? I'll think about that. That's a good one. That's a good one. You caught me there. Okay, so suppose P is not a divisor in A, but P divides A and A times B. So anyway, interesting. Yeah. Okay. Well, let me finish it the way I was planning to do it, and then I'll think about your question later. David.
Yeah. So A can be co-prime with B even if A isn't prime?
Yes.
That's cool. Seems weird, but it makes sense.
Why? Like 3 and 7 are co-prime. They're both primes. But 6 and 25 are also co-prime. Neither of them is prime.
It never really occurred to me to call something co-prime if it wasn't prime. It seems like it would be adding on.
You even call things co-prime in your daily life? Is that?
Well, I mean, I don't have that much experience calling things co-prime. I would say about 3 or 4 minutes, but you get the idea.
Okay, for those of you at home, he just confessed that he's only got 3 or 4 minutes worth of thinking about the calling things co-prime. But yeah, give it some time. Give it some time. It'll sink in. Okay. So anyway, suppose P isn't a divisor of A, then P and A are co-prime. That means you can find integers m and n such that ma plus np is equal to 1. Okay. Now what do? We multiply both sides of that equation by b. And you have m times ab plus n times pb equals b, right? And look, p is a divisor of the left-hand side. How come? P divides AB, that's an assumption, and P divides P. That means that P divides the left-hand side, which means that P divides B. Conclusion, if P doesn't divide A, it has to divide B. You do the same thing in reverse, you find that if P doesn't divide B, it has to divide A. So thus, P not a divisor of A, and this is a temporary notation, this is not something to take to the math bank, implies P divides B. Similarly, P not a divisor of B implies that P divides A, and that's the same thing as saying that either P divides A or P divides B or both. Okay, so those are examples of easy to prove things. That one over there is really important. So, like I said, write it down on a little business side card, keep it in your wallet, whatever. I guess you guys still use wallets, right? You don't pay with everything with your phone, right? You need cards. You need things. Yeah, okay. All right. Now, before we move on to modular arithmetic, one other general fact about integers, natural numbers, whatever. Yeah.
I'm not really seeing that MA plus N and P equals 1. Like, M and N are both natural numbers, right?
No, one of them actually has to be negative because both A and P are positive.
Oh, okay, so that's how you get one.
Yeah.
Yeah, that makes sense.
Okay. Yeah, good watchdog type question. Yeah. Okay, one more general fact, and this is probably better known to you all than either of these. You've heard this one before, but it turns out that to prove this properly, you have to use these other ones. So one more important fact. If n is any natural number bigger than or equal to 2, then n has a factorization of the form n equals p1 to the, I don't know what to call these things, p1 to the m1, p2 to the m2, up through, say, pk to the mk, where the p's are prime, so pj is prime for all j. The exponents are positive. This is a P1. And this factorization is unique in the sense that up to reordering of the P's, there's only one. Okay, so the mantra is every natural number bigger than or equal to 2 has a prime power factorization. And existence is really easy to prove using induction. Uniqueness, you have to use these other basic facts to do. Okay, and I'll leave that to the monograph. I won't go over the proof of that in class. You've all seen this before. You all know it before. David.
Can you just read that last sentence in terms of where, because I see semicolons and J's.
Where colon, Pj, I should have used some other index, I guess. Pj is prime for all j, semicolon. Mj is positive for all j, semicolon. And the factorization is unique up to the reordering of the p's. Okay? And this is something they probably told you back in grade school even. right? All right. Does anyone know how hard it is to find the prime factorization of a given natural number n in a computational sense? Okay, Ricardo? Okay, I think it's something. Well, let's be more quantitative. How fast does the complexity of the computation find the prime factorization of n grow in n? Actually, it grows linearly in n, but it grows exponentially in the number of digits of n, or number of bits used to specify n, which is really the way you specify data. Let's pose a simpler question, and this is going to come up later on. Suppose you know that n is equal to, say, p times q, where p and q are prime. Someone comes up to you in Ho Plaza and says, here's n. It's equal to the product of two primes. Find them for me. How hard is that? They're giving you a lot of information there. How fast does the complexity of that grow? Again, it grows linearly in n, exponentially in the number of digits in n. How does that work? Why does it grow linearly in n? Well, the only way that anybody knows so far to find p and q, even if they know in advance that n is equal to p times q, is by trying all the different prime numbers one by one by one by one until you find one that divides n. And of course, once you found one of them, you know the other one. You just divide p into n. The worst case complexity of doing that is linear in n. Alex? Is that true? Let's think about that.
Well, you only have to check.
Like 35 is 5 times 7, right? And 7 is bigger than the square root of 35. Yeah, you'd find 5 first. Yeah, well, it grows essentially linearly. That's all I know. You know, the only way to find it is by enumeration. Yeah, you can find the second one. Okay, if it's linear and the square root of n is still exponential in the number of digits. So that doesn't get rid of that problem. But anyway, it turns out this is really hard to do. And this is why, it turns out, is why, part of the reason why all this prime numbers, modular arithmetic, and everything turns out to be useful for cryptography. Because what we're going to see schemes where, in order to break a code, you have to solve that problem. Okay, well, we'll save that for later. All right, now I want to talk a little bit about modular arithmetic. Aiden, I think I just figured out the answer to your question, that it has to be less than or equal to at least one of A and B to divide their product, I think. It can't be bigger than or equal to both. So, because, yeah, as long as it's less than or equal to one of them, we can follow through with the proof I gave you. But anyway, okay. All right, so the next thing I want to talk about is I want to talk about modular arithmetic. And this is something, and my notation is going to be slightly unconventional here, but it turns out, in my opinion, to make the exposition a little smoother. All right. So here's some notation that's peculiar to this course. So it's non-standard. Suppose I'm given A in the natural numbers, and I'm going to assume A is bigger than or equal to 2 to make things non-trivial. Okay? This notation means, so, and m in the natural numbers, or m in the integers. This notation, and in the monograph I use a double brace or a double angle bracket here. I'm just going to use a single angle bracket in class to keep the chalk to a minimum. M mod A, that's how I'm going to pronounce that. That means the mod A value of m, or the value of m mod A, or whatever. What is that? Everybody has seen this before, so I'm just going to run through a few examples. If you're given any integer m, you can always write m as a sum of a's plus a positive or non-negative remainder. That non-negative remainder is what we call the mod A value of m. So for example, what is 3 mod 9? It's 3. What is 12 mod 9? Since you... That's 3. What is, say, minus 7 mod 5? That's 3 again. Does everyone see where I'm getting these? Please say no if you don't. Okay, good. What is 37 mod 17? 3 again. Okay, so the meaning of life is 3, right? Or 42 or something. 42, right? Yeah. Okay, how do we get all these? How do we get all these? The idea is you can always write m as follows. M is equal to Ka plus R, where K is an integer and R is a number that's bigger than or equal to 0 and strictly less than A. It's the same as that D thing we did a little while ago, right up there in the northwest corner of the board. R is equal to M mod A. That remainder, that non-negative remainder you get, is equal to the mod A value of m. So, for example, 3 mod 9. K is 0 and R is 3. There's only one way to do that. It's unique. What about 12 mod 9? K is equal to 1 and R is equal to 3. 12 is equal to 1 times 9 plus 3. 3 is equal to 12 mod 9. This one is the first weird one, the one where everybody said no. Minus 7 is equal to minus 2 times 5 plus 3. 37 is equal to twice 17 plus 3. So all these examples we got 3. What is a necessary and sufficient condition for m mod A to be equal to 0? Somebody besides you guys for this one. Manish. Yes. This is if and only if A is a divisor of m. Okay? All right, so that's notation we're going to use. Now here's some more slightly non-standard notation. given a in the natural numbers bigger than or equal to 2, the integers mod a, z sub a, so I refer to this as the integers mod a, that's just equal to the set 0, 1, 2, up through a minus 1. This is the set of all mod a values of all the integers. So it's the set of all, and this is practice using math notation, the set of all m mod a such that m is an integer. Okay, that's another piece of notation that's slightly non-standard. Now, on the integers, we have some operations associated with a. So, same context. In other words, a in the natural numbers, a bigger than or equal to 2. We're going to define mod a addition and multiplication on the integers and we'll see how it restricts to that as follows. If I have m and if I have m and n, m plus m plus n mod a is the mod a sum of m and n. M times n mod a is equal to the mod a product of m and n. Now, as it happens, mod a addition and mod a multiplication obey every possible rule that you could possibly want them to behave, to obey, which is really cool. And I don't want to sweat going through proving any of these things. I give you a sketch in the monograph. But suffice it to say that you can take sums and products and mods in any order you want. You have commutativity. You have of both operations. You have mod a multiplication distributes over mod a addition, blah, 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 blah. Everything you could possibly want to have be true is true. So it turns out mod a addition and multiplication behave sort of exemplarily. That is to say, how about if we do this? How about if we say like m plus n mod a plus q and take mod a? What do we get? We get the same thing as we would get if we took just m plus n plus q mod a. Or if we took m mod a first, n mod a second, q mod a third, added those all together and modded out by a. Hang on a sec. Is there a mistake here first?
The word in the first line, x,
turns out colon. Mod a addition. Oh, exemplarily. That's the adverbial form. Stephen King said the road to hell is paved with adverbs. Okay, but what he meant by that is you weaken your writing. You weaken your writing by throwing in too many adverbs. What's that?
You're missing an m.
Okay, spelling. The road to hell is paved with spelling adverbs incorrectly. Exemplarily. For example, all these things are true. And if I take, say, mn mod a times q, and then I mod a that's the same as, say, mnq, all producted first off modded by a. It's the same as the product of m mod a, n mod a, q mod a, and so on. As long as the last thing you do is mod out by a, everything works. Okay? So we never have to worry about playing with these things in any way we want. Okay, now here's an observation. If you look at the integers mod a, and think of that as a subset of all the integers, then what's true about that in terms of these operations of mod a addition and mod a multiplication? What's the mathematical term I'm looking for here? Maybe I haven't given you enough info yet. Suppose I take m and n and they're both in z integers mod a. Alex? It is a ring, but that's way beyond what I'm looking for here. As a subset of the integers, right, I can perform operations on guys in there. Ricardo?
An equivalence class?
No, not an equivalence class. That's way beyond. Justin? It's closed. That's all I was looking for. Yeah, exactly. That set is closed under these operations. So note, the integers mod a is closed under mod a addition and multiplication. Okay? In other words, if m and n are in z mod a, or integers mod a, then m plus n mod a and mn mod a are both in there as well. If you take two things in the integers mod a and you do mod a addition, mod a multiplication, you'll still get something in there. So we can think of these operations as restricting to operations just on the set z mod a, integers mod a. And I'm going to give those operations another piece of slightly non-standard notation. I'm going to define plus with a bar over it and times with a bar over it as respectively mod a addition and multiplication restricted to the set integers mod a. So all that means is for m and n in the integers mod a, if I write this m plus bar n, all that means is m plus n mod a. M times bar n equals m times n mod a. And now's a good time to take the 3-minute break. And while you're doing that, if you're bored, think about these operations on z integers mod a. Does either of them or both of them have an identity element? And are there additive inverses for everybody? Are there multiplicative inverses for everybody, or for some people? Some, whatever. Think about those questions.
How would you end up with an additive? Except for 0, I guess 0 is 0.
Okay, let's look at, this is just for you.
Yeah, you can. Except for 0. Well. Oh, wait, no, you could, okay.
What goes in here? Collage, got it, yeah.
Right. It is fine for you. In one page operator. Yeah.
Okay, that's good enough, I guess. I wonder if we're still on when the video note guy is out of the room. It's hard to tell. Oh, so they take out the break? Okay, yeah, I got it. All right. So we'll assume we're online, and I won't tell any secrets about prelim 1 for the folks who aren't here. Oh, by the way, that reminds me of something. I'm actually gonna post last year's prelims for you guys with the answers, because I know they're out there, and it doesn't bother me because I don't think you can replicate results by pattern matching. But last year there were some people who were a little uncomfortable about that because some people had access to them and some people didn't, and that didn't seem fair. So I'm just going to post last year's prelims eventually with answers. So you'll see what kind of a test it is and how it works. All right. So anyway, now we have these operations, plus bar and times bar on integers mod A. So does the plus bar operation have an identity element? Yes, what is it? 0. Thank you. So note, first off, 0 is an identity element for plus. Does the times bar operation have an identity element? 1. 1 is the identity element for times bar. Do we have commutativity and distributivity of these operations? Associativity? Yes. So all that good stuff is true. What about additive inverses for the operation plus bar? How many people think that every m in Z sub A has an additive inverse with respect to the plus bar operation? Okay, how many people think that not necessarily everyone? Okay, give me an example where it's not. Where you have Z mod A pick an A, and pick A small, you know, whatever. Pick an M in Z mod A, and you think it doesn't have an additive inverse.
No, I thought they all did.
Okay, they all did. You voted for. I thought you were voting against. I'm sorry. All right. How many people think that not everybody has an additive inverse? See, now I've given it away. Okay, why not?
Wait, let's say I mean, ZA is just 0. It's all positive.
They're all positive,
And,
but it's mod A addition, remember. It's not plain old plus.
oh, okay.
Get it? Hey. Okay. And over here, we actually talked about it down here during the break. Think about Z mod 5. I'm going to erase this one. Z mod 5 is 0, 1, 2, 3, 4, right? That's the definition of Z sub 5. If I take 2 and I modular add 3 to it, I get 0, right? So what's the general formula for the additive inverse of some M in, yeah, except 0, which is just the additive inverse of itself. So observe, if M is in Z sub A and M is not equal to 0, then M plus bar A minus M equals 0. And this is also in ZA because A minus M has to be less than A because M is positive. Which means that A minus M is the quote-unquote additive inverse to M in Z sub A for all M. So every M has an additive inverse. Yeah?
Well, this M have to not be 0.
Because A is not in Z sub A.
But doesn't.
0 is its own additive inverse. Okay? But this formula A minus 0 doesn't work for 0. That's why I wanted to get it.
Well, I get why you can't do. Why you can't do 0 plus bar A because it's not. You can't put A into that.
Yeah.
Okay. Yeah.
Yeah. All right, everybody has an additive inverse with respect to this plus bar operation. What about multiplicative inverses? This is a much more interesting question. IMHO. How many people think everybody in Z sub A has a multiplicative inverse, except for 0? 0, of course, doesn't have one. Okay, there's 2, 3. Okay, how many people think that it's possible that some non-zero things do not have multiplicative inverses? Okay. Well, it turns out that that second group is correct. That there are cases where you don't have multiplicative inverses for every non-zero thing. And let me give you an example. So let's first pose the question, what about multiplicative inverses? So what about quote-unquote multiplicative inverses? I.e., for M in ZA, when can we find some K in ZA such that M times bar K equals 1? That's what I mean by when does M have a multiplicative inverse. Let's think of an example. Let's look at Z4. That's 0, 1, 2, 3. First off, we need m not equal to 0. So we're only going to be looking at non-zero things here. 1. Does 1 have a multiplicative inverse? Yes. And what is it? It's 1. Okay. So 1 has a multiplicative inverse itself. What about 3? Does 3 have a multiplicative inverse? Yeah. 3 does too. 3 times bar 3 is 9 mod 4 equals 1. So 3 is also its own multiplicative inverse. Itself. What about 2? Does 2 have a multiplicative inverse? Can you prove it? Okay.
Well, I mean, if you take if M and N are co-prime, then MA plus NB equals 1 for some A and B.
You're working way too hard. Let's look at this simple example. What's an easy way to show that 2 does not have a Ricardo?
Try 2 times 0.
Yes, exactly. 2 times 0, no, that's not 1. 2 times 1, no, that's not 1. 2 times 2, that's 0, so that's not 1. 2 times 3, that's 2, that's not 1. Conclusion. There is no guy in here that when you multiply it by 2 with a bar over it, you get 1. So that's you were proving the general result, okay? He was doing the engineer thing. Not an insult. Compliment. Okay. So bottom line is, so note that 2 times bar 0 equals 0, 2 times bar 1 equals 2, 2 times bar 2 equals 0, 2 times bar 3 equals 2, which means that 2 has no times bar inverse in Z4. Okay. So, interesting question. Interesting question. What things in Z4 or ZA in general have multiplicative inverses? Here's the fact. First, I'll give you some notation. No, I'll give you the fact first. So here's a fact. M in Z sub A has a multiplicative inverse. And remember, I'm talking about this multiplicative as being mod A multiplication. So it's with respect to times bar. And this abbreviation, by the way, WRT, with respect to, is everyone familiar with that? Has everyone seen it? Because that comes up quite often. I think I used it in 2200 last spring. If you ever read anything by David Foster Wallace, you'd see that up the wazoo. But anyway. M in ZA has a multiplicative inverse with respect to times bar if and only if what is true. You were about to tell us a minute ago. Yes, M and A are co-prime. No common factors. Okay. Why is that the case? I'll prove one direction of it and leave the other one to the monograph. I'll prove what I consider the easier one. Is there something missing or incorrect or? Okay. If M and A are coprime, then by the huge important fact, huge important useful fact, or was it huge useful important fact, I forget, we can find, say, let's call them K and L in the integers such that Km plus La equals 1. And this is not plus bar. This is regular old addition. Okay? Now, what do? We mod out both sides by A. On the left, we get Km plus La mod A. On the right-hand side, we just get 1 again. Now, what happens when I mod out the thing inside the mod A sign? What disappears? The LA, because any multiple of A is mod A equal to 0. So this means that Km mod A equals 1. And because modular multiplication, mod A multiplication, works in every possible conceivable way that you would ever want it to, we can rewrite this as K mod A times M mod A, which is just M, mod A equals 1. And this is the same as saying that K mod A times bar M equals 1. Therefore, M has a multiplicative inverse, and we just calculated it. The converse of this is also pretty easy to show. I'm just not going to go through it in class because I think it's kind of boring. It's in the monograph. So thus, M and A coprime implies that M has a times bar inverse, and see the monograph for the converse. Okay. All right, so now that, yeah.
Sorry, how do we know
No
that
problem.
M mod A is?
Because M is already in Z mod A to start with. Got it? Okay. Here's some notation. I'm going to let ZA star be the set of all M in ZA such that M and A are co-prime. This piece of chalk is not behaving well. So, in other words, it's the set of all M's that have multiplicative inverses. That turns out to be a really important set of numbers. And anyone who's ever taken an abstract algebra course or read a website or whatever about it, Alex brought up earlier that Z sub A turns out to have the structure of a ring, a commutative ring. And this is called the group of units of this commutative ring. That's what it's called. Alex. Everyone has an additive inverse. Oh, no, you don't have an addition operation anymore in that case. Yeah. You only have the addition operation when you're looking at all of Z sub A. All right. The number of things in Z mod A star we call phi of A. Phi of A is equal to the number of elements in ZA star. And that's standard notation. phi, this phi thing, there has various names. Does anyone know what it's called? There's at least two names for it. Totient function, that's one name for it. Another name for it is a little bit more boring, prosaic, whatever. It's a guy's name. Plus, yeah. Yeah, Euler's phi function. That's what everyone calls it, you know. Euler's phi function or Euler's totient. You know, that's what, see, on Ho Plaza, if you went up to a random person and said, define the totient for me, you know, they wouldn't know what you were saying. But if you said, define the Euler's phi function, then they would know. Okay. So the names for phi. Right, right. We won't always use Ho Plaza. Like, there's other places to run into people at Cornell, right? Like under the cantilevered part of Milstein, say. What are you guys arguing about?
We're wondering, like, if we actually tried it, would it work? And we're thinking we'll probably just someone will try to sell us their mixtape.
That guy in College Town isn't here. Is mostly downtown now this year.
Okay, good. Oh, really? He was annoying.
No, like I just got to a rhythm with him where we would fist bump as we went by, you know. And actually Sunday I went down and visited the rebuilt Commons for the first time, you know, and it's pretty nice. And I was walking down the Commons and there he was with his, you know, CD playing, and he fist bumped me, so I thought that was cool. And he said, "Good to see you on the Commons." Yeah.
Have you ever listened to the CD?
No, I haven't.
Not a good idea.
Well, I know it has a lot of, from listening, it has a lot of N word, and it has a lot of F and MF, and
It drops off past there too.
yeah, okay, yeah, not good. All right, so phi of A is called the totient function, or Euler's phi function. And we've defined it as the number of things in Z sub A star, but a more elementary definition would just be it's the number of m's such that 0 is less than or equal to m is less than a, and m and a are coprime. Okay, so that's Euler's phi function. And Euler's theorem, which turns out to be the key for all the cryptography stuff that we're going to be talking about. And by the way, Euler was a really important mathematician, and he proved a lot of theorems. And so, like many different fields of math have an Euler's theorem. So if you type it into your search window, it'll be like disambiguation, you know, Euler's theorem in number theory, or Euler's theorem in physics, or what, you know. I think it'll probably come up. But this is the one, this is probably the most famous one. Euler's theorem goes as follows. If m is in ZA star, then m to the phi of A mod A equals 1. Another way of writing that is m times bar m times bar m times bar dot 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 times bar m, where this product is phi of A times equals 1. So the mod A power of m to the phi of A equals 1. That's Euler's theorem. At least that's one form of Euler's theorem. Okay? Turns out this is really important. Now, I'm not going to prove this in class. It turns the proof in the monograph is kind of group theory in disguise, if you want to look at it. So there is a special case of this that I'm going to show you part of in class, and you're going to do the rest of it on your homework. But let's consider a special case, just to see if we're on the same page here. You have a question? Someone? Anyone? All right. So just to make sure we're on the same page, let's do a little reality check. Suppose A equals a prime number P. Okay? What is ZP? ZP is 0, 1 up through P minus 1. What is ZP star? Go ahead. Ricardo says it's 0 and P minus 1. How many people think that's ZP star? What is ZP star? ZA star for any A is the set of all guys in ZA relatively prime to A, co-prime to A. Varun? All of them? Remember, everything's a divisor of 0. What's that? Not quite. 0 is not in there. ZP star is, remember, ZP star is the set of all things that are co-prime with P. And that never includes 0, because 0, everything is a divisor of 0, including P. And it's also, by our theorem, it's everything that has a times bar inverse, right? And 0 can't have a times bar inverse, right? So this is 1, 2, up through P minus 1. In other words, every non-zero integer between 0 and P, not inclusive, is co-prime with P, and therefore is in ZP star. Okay, well, we'll pick this up next time and see how it applies.